Welcome to another Learning Together session sponsored by the Brosis Foundation. We are delighted to provide week after week, to provide you with lessons in math and also in English. And what is the purpose of all these things that we're doing? We're just providing extra resources for those who might have need, even if it's just a need to have a different look at something that you have already been exposed to. So that's the purpose. We're just providing additional resources. And it might so happen that this might play a critical role for some people. Today, we're going to start exploring a section of math that many students graduate from high school and never, ever got into. It's called set theory. Just recently, we completed matrices. That's another topic that many students never saw in high school. Well, we have covered matrices over about 3 sessions. Today, we're going to start set theory, and we will cover at least 2 sessions for set theory. So today, I'm just going to lay the foundation, define some terms, and then take it from there. So what is set theory? Set theory is a concept of math that deals with grouping information in groups that we refer to as sets. So for example, in a high school, you could talk about the set of all freshmen, the set of all sophomores, the set of all juniors, the set of all seniors, or you could say the set of all 7th graders, the set of all 8th graders, or the set of all girls, the set of all boys, or the set of all 13-year-olds, the set of all those that are 12 to 15 years old. That type of stuff. If you're dealing with, say, for example, cars, you could talk about the set of 2-door cars. Then you could have the set of 4 doors. Then you could have the set of SUVs. That's the idea. So a set is just a group of items that are identified in a particular group. And the items do not necessarily have to have a relationship. They could just be random items put together to form a set. For example, you could be in a class of, say, 30 kids, and they decide, okay, you're in that first set, and then another group in another set. Okay? Or if we come to numbers, and say we're dealing with the numbers, say the numbers 1, 2, 3, 4, 5, all the way to 10. I will start by telling you that these numbers that are in this set are often enclosed using the curly bracket to say that that is a set. And it's often given a name. And we normally use an uppercase letter to name a set. So you could say that this is a set A equal. Then I could say the set B is equal to 2, 4, 6, 8, 10, 12, 14. Then I could say C is a set of numbers 1, 3, 6, 8, 9, 11. These, there's a pattern, is a set of all integers from 1 to 10. This is a set of all even numbers from 2 to 14, inclusive. This doesn't seem to have any pattern or any relationship, any connection between the items within the set, okay? And then later on, we can do comparisons among the sets A, B, and C, and we'll get there. So again, you could denote a set by listing the members in the set, which we call elements. So each item is called an element, okay? So this one has 10 elements. This one has 1, 2, 3, 4, 5, 6, 7 elements. And this one has 1, 2, 3, 4, 5, 6. Okay, so now you're starting to get an idea. The element is each item within the set, okay? And the set is often grouping the numbers and enclosing them with curly brackets. Got it? We also name sets by using uppercase letters. All right? Now, suppose in this situation, we're saying that our sets can only include numbers from 1 to 20. So the only numbers that could be considered are the numbers 1 through 20. Then the set of numbers 1, 2, 3, all the way up to 20 is called the universal set. Those are the only items that could be considered within this application, if that was the case. Okay? So suppose we're talking about, say, Brosis High School, the set of all students at Brosis High School. Then if there's a student at Green Island High School, then that person would not be in the set of students from Brosis High School. Okay, now you're starting to get it. Okay, or if we said that we are only going to consider students who are in 9th grade, then a student in 7th grade could not be in that set. A student in 10th grade could not be in that set. So the 9th grade students would form the universal set. So the universal set restricts us as to what we could consider when forming what we call subsets. So the subset is a portion of the universal set. Okay? So in this case, if we're dealing with the numbers 1 to 20 as our universal set, that is our, you could say that's all the options that we have. Then this A is a subset because it's taken from the universal. This also is a subset. It's part of the overall. This again is another subset. Okay, so now we are starting to enlarge our concept of set theory. So I'm going to back up now and start making some definitions. I've hinted at some things, but I'm going to start documenting some of the items. Okay. So, a set is a collection of items, and the items do not necessarily have to be related. They could be random. So that's what a set is, okay? So there could be a pattern, or it could be just random, arbitrary, okay? So we did mention this before, that we use uppercase letters to name sets. So we use uppercase A, P, M, Q, whatever letter you choose, but it's a practice to use uppercase letters, okay? So the set of all possible items that can be considered in a specific situation or specific application is called the universal set. So suppose we're playing with numbers and I say, okay, let the universal set be all numbers from 1 to 25 inclusive. And then from there, I start list some other sets related to the universal set. Okay? So what will happen from there is portions of the universal set are called subsets. So you have the universal set, which is the overall, the complete set of items, and then subsets would be a fraction thereof. Okay? And we refer to individual items, dimension. The individual items are called elements. In a set called elements. So the individual items within a set, we call them elements. Okay, so a set might have 5 elements or 5 members. Another set might have 7 elements or 7 members. Okay? And then we mentioned subset. So let's use an example and let's go. Example. So if you were to describe the universal set, it's the set of all integers from 1 to 15, inclusive. What does inclusive mean? That the end numbers are also included. So 1 to 15 inclusive, meaning 1, 2, 3, da 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 da, all the way up to 15 are the options available. Okay? Okay, so U is our universal set. What is that? These are the only numbers we're going to consider for this application, for this situation. Okay? You can see that A is derived from a portion of the universal set. B is also derived from a portion, similarly with C. So A, B, and C are all called subsets of the universal set, meaning that they are a fraction of the whole. Now, the subset could be the entire universal set. I could have named another set D that has all the numbers 1 to 15. What it means then is that D is equal to the universal set. So just keep that in mind, that a subset is a portion or all of the universal set. Technically, the term subset is often used when we're only dealing with a portion of the whole. Okay, but keep in mind that U, say D having all the numbers 1 to 15 is still a subset of U, because everything that is in D is also in U. That's the criterion. For D to be a subset of U, every element in D must also be in U. So if all the elements in U are also in D, it still satisfies the condition that the elements of D must be in U for D to be a subset of the universal set. Wonderful. So now I'm going to share with you some operations in set theory. Okay? We realize here that set A has elements 2, 4, 6, 8, a total of 1, 2, 3, 4, 5, 6, 7 elements. B has 1, 2, 3, 4, 5, and C has 1, 2, 3, 4 elements. So now we could talk about a union of two sets. Okay? And as a matter of fact, before we do that, we could say that A is a subset of U. What does it mean? It means that everything that is in A is also in U. A is derived from U. Okay? We could also say that C is a subset of A, because everything that is in C is also in A. 2 is there, 4 is there, 8 is there, 14 is there. C is also a subset of U. So far, so good? Okay, good. So now, here goes. If you want to merge, bring together sets B and C, there is a symbol used for that. It's called the union. And the union of two sets is when you combine the elements of the two sets. One thing to keep in mind, when you form the union, you do not duplicate one that is in both. You just write it once. So for example, B union C. Notice B union C is equal to the set. So you go to B and C, and you notice it's going to be 1, 2, 3, 4, 6, 8, 10, 14, 15. So the union of B and C will be 1, 2, 3, 4, 6, 8, 10, 14, 15. Notice I put it in numerical order. That's for ease of reference. It's not a requirement, but aesthetically it looks so much better. If you can go, and if, for example, you're doing comparisons, it's easier if it is in numerical order. Okay, then we notice that even though B and C, in this case, actually, nothing was duplicated. So, yeah. We also notice that A union C is actually equal to the set A, because everything that is in C is also in A. So therefore, when you do the union, you still get A. because there's nothing in C that is not in A. Okay, so that's the union. The union is what happens when you combine, when you merge two or more sets. So you could have talked about A union B union C. So you're combining all three sets. Okay, great. We're not going to do that, but I just want to let you know this is a thing. It's actually valid. Okay. So just as we talk about the union, we can talk about, so the union is a merge. You're merging two or more sets. So now we're going to go to another phase, which is called the intersection of two sets. So let's go, this one is intersection. So A intersect B. So we use the upside down U. So the union is the merger. This is the intersection of A and B. This is referring to the elements that are common to both A and B. Where do they overlap? That's the word intersect. They have the same things in common. So when we go to A and B, we notice not 2, not 1, 3, no, 6 and 6. Anything else? 8 and 10. Oh, 10 and 10. I see we're doing A and B, and that's it. 6 and 10 represent the intersection of A and B. So far, so good. Let's go to B intersect C. B intersect C. Just want you to know that this operation is commutative. In other words, A intersect B is the same as B intersect A. It doesn't matter which one you write first. The fact is, are those items in both? If the answer is yes, then there is an intersection. If the answer is no, then there's no overlap, there's no intersection. So let's go to B intersect C. What do we have? 1, no. 3, no. 6, no. 10, no. 15, no. There is no overlap. When that happens, we end up in something special. It's called the empty set. Another name for the empty set is, another symbol for the empty set is like that, like an O with a line through it, and it's also called the null. Null set or empty. So let's make sure we get that clear. If there is no overlap, there's no element common, then we say that it's an empty set or a null set. Okay? Good? Excellent. Again, all we're doing today is just laying a foundation. So we have identified the universal set. We have identified what elements are. We have identified what the union of two or more sets, what it creates, and how to create that. And we have also discussed how to find the intersection of two or more sets. Okay, good. Let's do another one. By the way, I would like to put another set here. Let's call this D. So D is a set with two elements, 4 and 10. So if I'd asked you, what is A intersect B intersect C? Okay, now, what am I looking for? I wonder, what would make sense? What do you think, based on the definition using two, what do you think we're doing now? I want to suggest that this is asking us, what is common to all three sets? Are there any elements that are found in A, B, not C, I wanted to do D, sorry. Well, since I wrote it, let's stay with that. I'll do this as a different one. Oops, that's ugly. Okay, ready. Is there anything common to A, B, and C? Well, we already discovered that B and C have nothing in common, so therefore all three would have nothing in common, or a null set, empty set. However, when we go A, B, and D, what do you notice? Well, it's best to start with the smaller set. You have less work to do. 4. Is 4 here? No, it's not. So you don't even have to look further. You stop. It's not. And it's not in the intersection. 10. Is 10 here? Ah, yes. Is 10 here? Ah, yes. So 10 is in all three. So therefore, there is a yes. And that will be the intersection of all three elements. I mean, all three sets. Okay? Pretty cool, isn't it? Okay, let's continue the exploration. Okay, so let's call that A, and let's call this PQ. Let's call this let's call this set G, and I'm going to use this as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, remember we said the universal set is a set of all elements that we can use. So in other words, 16 could not be used because 16 is not in the pool of items that we're considering. Right, so new term. The complement of a set. Now, when you hear the word complement, the English teachers in my midst would say, wait a minute, complement is spelled C-O-M-P-L-I-M-E-N-T. Complement, when you're giving somebody a favorable feedback, compliment. But that's English. This is math. Math uses the word complement to refer to, for example, if I ask you for the complement of A, you have A, that's the original set. A complement is A with a superscript. A dash as a, well, a stroke as a superscript. It is equal to the set, it's equal to the set of all items that are in the universal set, but not in A. The set of all items in the universal set, which are not in the set A. So this is A. So whatever is here, but not here, would be in A complement. So in this case, the answer would be 1, 3, 5, 7, 9, 11, 13, 15. So this was a set of all even numbers. So this would have to be the set of all odd numbers. Yes? So on that note, what is the complement of the set G? What is the complement of the set G? What you would have to do is, well, G goes from 1 all the way to 10, but the universal set goes from 1 all the way to 15. So therefore, the complement of G must be the numbers beyond 10 up to 15. So the answer would have been 11, 12, 13, 14, 15. There it is. So we have done union, we have done intersection, and we have done complement. Okay, I made a list of some topics that I wanted to cover, and we're making good progress. Okay, good. So I'm gonna need some space. So let's do this. By the way, a set could be described using words if they happen to have a relation. If they have something common that could identify them, or you just group them together in curly brackets. For example, I could say to you, A is a set of even numbers. Okay, even numbers from 4 to 10. So that's pretty explicit. The set of even numbers from 4 to 10. So therefore, you know, that could also be written as A equal to, or we could just list what the numbers are, 4, 6, 8, and 10. So all I'm trying to say here is you could have a descriptive expression for your set, or you could just list the elements in the set. If your universal set was a set of all numbers, all integers from 1 to 100, it would be kind of tedious writing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, all the way up to 100. That's a waste of time. So set theory allows you to describe what your elements are in words. Okay? Good. Okay. Now I would like to deal with what is called the Cartesian product. If A is equal to 1, 2, 3, 4, and B equal to X, Y, and Cartesian product AB is it's going to be equal to the set of all pairs where this so it's going to be the set of all pairs where the first number comes from the A, the second number comes from the B. Now watch this. If I switch this around to B times A, then it becomes something different because it means that the first entry has to come from the set B and the second entry would have to come from the set A. So in this case, the Cartesian product A times B is going to be equal to the set 1x, 1y, 2x, 2y, 3x, 3y, and 4x, 4y. That's what the Cartesian product is. If I go for B times A, the result is going to be different. This one, the letters will be first and the numbers will be second. So it will be x comma 1, x comma 2, y comma 1, y comma 2. Oops, 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 oops. x1, x2, x3, x4. So we have exhausted the x. Now we go to y. y1, y2, y3, and y4. So we have just defined the Cartesian product, okay? And I think there is another, okay. So what we also have is what we call ordered pairs. Ordered pairs. There is a concept in math that deals with relations and functions. Relations and functions. For example, you could have input let's not make this 3, let's put another number. Okay, so that's a relation. It's also called, this is now called a mapping diagram, showing that these terms are associated with these terms. So this is called a mapping diagram, and it can also be represented as a set. It will be the set 2, 0, where the first is input, the second is output. Then also 2 is associated with 6. And then 3, -4. And then 5, 7. So this is what you call a set of ordered pairs. This is a mapping and then, of course, you could have what is called the input-output table. We have 2, 0, 2, 6, 3, -4, 5, 7. So that's 3 different representations of the same information. And then, of course, you could also call this an XY table. Input, output, or X, Y table. But the first item is X, the second is Y. Okay? And then, of course, the third thing you could do is you could represent these on a graph where two, 0. So we have 1, 2, 3, 4, 5. And then here we have 1, 2, 3, 4, 5, 6, 7, 8. Now we have 1, 2. Now we have 2. 1, 2, 3, 4, 5. So each is a point. 2, 0 is a point. Then 2, 6 is another point. Then 3, -4 is a point. And then 5, 7 is the next point. We have 1, 2, 3, 4. 1, 2, 3, 4. So we have 1, 2, 3, 4 different ways of representing this relation. Okay? And just as a little extra that I'm adding to this is, this relation is not a function because this input has 2 different outputs. In order for it to be a function, each input must only have 1 output. An input cannot have multiple outputs. So it's just a relation. But if it was such that the input here only has 1 output, then it would be also a relation and also a function. That is extra. I just want to put that out there so you'll be aware of it. Okay? Good. So let's come back. So we just dealt with the ordered pair. That's the ordered pair right there. So sets are represented using Venn diagrams. V-E-N-N. Venn diagrams. Okay? And the best way to explain what a Venn diagram is to draw a Venn diagram. So let's set up a scenario and let's take it from there. Suppose we have U equal to the set 1, 2, 3, 4. Let's use letters. We have been using numbers. Let's use letters. So U is a set of the first 10 letters of the alphabet. Okay? And if I ask you to represent this information as a Venn diagram, what you do is the universal set will be in a rectangle. So this is your universal set. That's your U. And then your subsets will be in circles. Watch this now. And if perchance your subsets have overlap, meaning that they have something in common, then you make your circles so they intersect. So this is, I need more space for B, so I'm going to put B here. I'm going to put A here. Now, you can actually put U and put 10, where that means that there are 10 elements in U. B, you have 1, 2, 3, 4, 5, 6. So it could be B, 6, and A is 3. All those numbers are doing, they're just giving you the magnitude. They're telling you the size of your sets. Okay? Good. So now we need to place our elements appropriately. According to this, the overlap we have for A and B is A and E. So A and E go in the common area because they are both in set B as well as set A. They're common. So they're in the intersection of the two sets. Now, here would be the set of elements in B that are not in A. So what are they? They would be B, G, H, and J. Let me double check. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Yes. Now A has 1, 2, 3. I have 1, 2. So I need to put I over there. So then my question to you is, where do you think the elements in U that are neither in A or B, where should they be found? Should they be found inside the box or outside the box? Inside the rectangle or outside the rectangle? Well, I want to suggest to you that since U represents the rectangle, then all the elements that belong to U must be inside the rectangle. And since there are elements that are in U that are not in A or B, then they should be somewhere inside the rectangle, but not in either of these circles. So what do? Well, I think we have C. I think we have D. I think there are 4 that are missing. What about F? And what else? What else? What am I missing? I, J, 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 J. A. A is common. B. Yes. B. Oh, B is here. A, E, 1, 2, 3, 4, 5, 6. Oh, B is here. Okay, okay. F, 1, 2, oh, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh, we have covered all of them. A, B, C, D, E, F, G, H, I, J. Got it. Okay, so that's your Venn diagram representing that scenario. Okay, and you can see that I was able to account for all 10 elements. All 10 elements are accounted for. Okay, so here's my trick question for you. Suppose I ask you this question. Find what do you think that means? B complement intersect A. What do you think that means? Well, what is B complement? It's the set of elements in the universal set that are not in the set B. So what would those be? Well, we are 6 here, so it will have to be the other 4 that are not in B. But of those 4, are there any of them that overlap with A? And the answer is yes, I. So there's one item in the intersection of A and B complement. Let's try another one. What is B complement union A? Yes, B complement union A. Well, that's going to be equal to items that are not in B plus the items that are in A. So, what are the items that are not in B? Well, the answer would be C, D, F, and I. All the items that are not in B are here. And there's nothing in A that is not in B complement. There's nothing in A that is not in B complement because the I is also part of B complement. So that's the union. So that's what that would be. Now, suppose I ask for this one. Suppose I ask for A union B complement. Okay, so it is A union B would be all of these. So that would have to be the set C, D, F. A union B would cover all of these. And the complement of that would be what is not in the union. So this, and this. Okay? That's it. So that takes care of that. So I wonder if we have enough time to do one more example. One more example. So I've given you the universal set. I've defined 3 subsets, and your task is to find or to create the Venn diagram. Okay, so let's go. B is 2, 4, 6, 8, and C is 6. So between B and C, we have a 6 here. Oh, but it's also in A. Okay, cool. So if I'm not mistaken, I think 6 is in all 3. Okay. So let's go one more time now. So what else do we have? B has 2, 4, 6, and 8. And therefore A has 2, 4, 6. So therefore 2 and 4 will be in that section with A and B. 2, 4, and then the 6 is here, which is also in C. And then for A and C, we have the 3, the 6, 3 and 6. So there's a 3 right here. And then for C only, we have 9 and 10. 9 and 10 are not in those. So we have 9 and we have 10. For B only, we have 2, 4, 6. 2, 4, 6. So now we have 8. And for A only, we have 1, 2, 3, 2, 3, 4, 5, 6 covered, and 7. So the question is, what is not covered? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So all the elements are either in A, B, or C, or a combination of 2 or more. Okay? Now if I ask you to find suppose I ask you to find B union C intersect A. So B union C would cover all these items. And then you want where that intersect with A would be 2, 4, 2, 3, 4, 6. So that would be 2, 3, 4, and 6. Got it? B union C would be all of these. And you're looking for where they intersect with A. So the intersection with A will take care of these 4 items. Okay? And another one, if I ask you for A union B union C complement. So A union B union C complement, what is neither in A, B, or C? The answer would be the empty set or the null set. Because everything that is here is found in either A, B, C, or a combination thereof. Okay? I think in terms of definitions, we have made a great start, and I'd like to stop right there for today. And the next session, we'll pick this up and finish it off. Okay? Thank you so much for joining us. And on behalf of the Brosis Foundation, we thank you for joining us and sharing this time with us. We hope that you found this interesting and different, but be proud because now you are exposed to a concept that many students of mathematics do not get exposed to. This is a part of what is called the new math theory. And this specifically is called set theory, and it has a lot of useful applications in mathematics. Thank you so much for joining us, and enjoy the rest of your day.